Can everybody hear me? Okay. My name is Alexei Bylinskii, and I'm the head of quantum computing services at QuEra. Today I will tell you about two breakthrough theoretical results that will hopefully help us scale neutral atom quantum computers to the fault-tolerant regime in a resource-efficient way, meaning that we hopefully will be able to use much fewer resources in time and in space in order to do error correction and get to utility scale applications sooner. Oh, I might have turned it off. Sorry.
Just keep it on. Yeah, it's on now.
Oh, okay. Oh, I was pressing the wrong button. How do I get it? Oh, there we go. Okay, my apologies. Okay, there we go. So first, a little bit about QuEra. Our mission is to accelerate innovation by building useful, scalable, fault-tolerant quantum computers. We are a Boston-based startup, spin out from Harvard and MIT, with about 50 or so engineers and physicists working on developing, commercializing quantum computers based on neutral atoms, neutral atom qubits. And most importantly, we are a full-stack company, which means that we really deliver a full-scale, full-stack solution, starting with hardware, software, and ending with application development. The products and services that we offer today are all centered around these kind of full-scale quantum computing solutions, full-stack quantum computing solutions, starting, of course, with the machines themselves, the quantum computers that we build in the form of on-premise machines, but as well as cloud access, remote, compute time, software tools such as SDKs, simulators, compilers, and finally, we engage our customers and users in co-development projects to make hardware-efficient algorithms and applications. Of course, all of these efforts are centered around the actual quantum computers we build, and we have two types, the analog and the digital, which again can be on cloud or on-prem. The first generation machine is Aquila. It has been on the cloud since November 2022, so running for 2 years now at 130 hours a week, up to 99% uptime. And this 256 qubit analog machine is suitable for quantum simulations, optimization, and machine learning type problems. Our generation 2 machine is a digital mode or gate-based quantum computer with 100 plus physical qubits. And that is actually the baseline for our QEC roadmap towards large scale and fault tolerance. In 2025, we'll be launching 2 instances of that generation 2 machine. Actually, both will be on-prem installations. One is a full-stack quantum computing system going to AIST in Japan, and focused on application development. And the second machine will be installed at the NQCC in the UK as a developer testbed. And we hope to use both machines and other machines that we have at QuEra for doing co-development and for offering cloud access to these gate-based neutral atom quantum computers, which we hope over time will offer larger and larger scale and more fault tolerance as we implement some of the things I will tell you about right now. Now, we do believe this takes a village. We have started the QuEra Quantum Alliance this year, and we already have a number of partners who have joined. A lot of them have been using our analog machine through the cloud. We hope to add a lot more partners as we launch and develop our digital machines. And hopefully you come work with us and partner with us. Now, let's dive right into the error correction topic. So, of course, as you know, the physical error rates today are significantly different from the targets that for the encoded logical qubits that we need. And error correction is the way to bridge that gap. It's the only way we know today how to bridge that gap. And in a nutshell, error correction is various approaches to using a collection of physical qubits to encode some number of logical qubits in the way that errors on the physical qubits can be detected and corrected without disturbing logical information. And the power of the error correcting code is typically quantified by the code distance d, And as the code distance d grows, typically you can suppress the logical error exponentially, but it costs you time of the computation, and it costs you physical qubits or space to implement it. Now, this space and time resource, these are the two resources you need to kind of spend on having fault tolerance. And this analysis here shows on the x-axis runtime and on the y-axis physical qubits required for these various application areas, factoring, quantum chemistry, quantum dynamics. And you can see that if you look at the useful computation times, and if you look at the sizes of systems that would be accessible in the next 3 years for neutral atom quantum computers on the y-axis, you'll get this gray rectangle in the bottom left. And as you can see, it's still far away from many of these kind of interesting, useful scale applications. And so this talk is all about these two results that show that using a new approach to fault tolerance, the algorithmic level, you can hopefully shift this whole diagram to the left by a couple of orders of magnitude and shift it down by a couple of orders of magnitude if we use these algorithmic fault tolerance approaches and quantum low density parity check codes. Now, if all of this can be implemented practically and both at the same time, you can start to think about the top right corners of all these different application areas moving much closer to the near-term, accessible, useful compute time implementations. Now, of course, all this has to be demonstrated on hardware, but today I will tell you a little bit about the intuition behind these new algorithms. The results I'm talking about, the details can be found in these two archive papers. This work was collaboration between QuEra, Harvard, and Yale for the first paper with the important prerequisite paper on correlated decoding, and the second result was teamwork between Harvard, Chicago, and QuEra, and it's actually already been published in a peer-reviewed publication, Nature Physics. Now, it's very important for both of these techniques, certain features of the neutral atom platform that are actually kind of unique to the neutral atom platform. And here's a simplified summary of these features. So first of all, the qubit itself is encoded into the electronic wave functions of the atom. The atom can be trapped by an optical tweezer in 2D. It can be manipulated, configured, and reconfigured. And in fact, this reconfiguration can be done dynamically in the middle of quantum circuit execution without losing coherence of the atom, and that's the essence of shuttling. In addition, these physical qubits can be operated on in parallel in blocks, both for motion and for the gates, and that itself is very important for the transversal gates, and that's the key ingredient of both of these techniques I'll tell you about. And finally, zoned architecture allows us to move qubits between the zones and only have enough channels, have only one control channel or a few control channels per zone as opposed to per qubit. And that makes the control of the quantum computer significantly more scalable at scale. This architecture, the zone architecture, was demonstrated and made a big splash last year. And this is this machine is actually a machine that was developed at Harvard, and this is where these large logical algorithms were demonstrated in a paper last year in collaboration with QuEra. Now, again, the important aspects of what enabled this architecture was this non-local connectivity enabled by shuttling and this parallel efficient classical control that makes things parallel both for motion and for gates. This is an example of an algorithm running on that machine. You can see the two zones, the storage and the entanglement zone. You can see the parallel operation, the parallel motion of blocks of qubits. You can see the parallel application of 2-qubit gates in the entanglement zone. And you can see these transversal gates being done basically on logical qubit blocks. So all of these ingredients are here, and this gives you a nice visual of how that actually works under the hood. Now, let's dive right into this algorithmic fault tolerance idea. It's a new paradigm for fault tolerance, and it promises this factor of d speed up relative to conventional methods. Now, what is conventional methods? That's basically the idea that you need to make each operation in the circuit fault tolerant, meaning that you do a gate, then you do syndrome extraction to figure out if there are errors, and then you correct. And because syndrome extraction is an error-prone process, typically you need d rounds of error correction after every operation. And d typically for low enough logical errors is in the order of 10 to 30. But you don't actually care as a user of the computation to make every operation fault tolerant. What you care about is for your computation to be fault tolerant, meaning that you really only care about the classical output at the end being correct or being from the correct distribution. So now if you think about fault tolerance at the scale of the whole algorithm, or at least at the scale of very large computational blocks up to any kind of measurement and feed-forward operations, it turns out that by using transversal gates, you can really make the requirement of d rounds of syndrome extraction after each operation to be redundant. You can really do away with, you can really make this computation fault tolerant with only a single round of error correction per operation. And that, in fact, works for universal quantum computing, so universal circuits, and that's the essence of that result. Now, I did say that you need the transverse gates to make that work, and that's important because neutral atoms really can implement transverse gates very efficiently. And the reason why it's very important is because, number one, errors don't spread within the logical code block when you do transversal gates. So if you go from these checks in this slice of time in these two logical blocks, you go to the next slice of time, an error on one of the qubits that affect this syndrome really doesn't spread. It just goes straight up to the next slice in time. And when you have a 2-qubit gate that has an error before it, then you actually copy the error to the syndrome, the corresponding syndrome in the other logical other logical code block, but now these errors are correlated. And these correlations actually allow you to identify syndrome measurement errors and allow you to track deterministically these errors propagating through the computation. And by constructing decoding hypergraphs that span the duration of the logical code block or the entire computation, you can really, by decoding that hypergraph, you can really make the computation fault tolerant with using only a single round of error of syndrome extraction per time slice. And so this is the essence of this finding. So let's do a quick numerical experiment here. So this is a, you fix the physical error rate and you target a fixed logical error rate, and then you run deep random Clifford circuits with syndrome extraction after each layer. And then you can vary the number of syndrome extraction rounds. And if you optimize for space-time cost, meaning what is the depth of the error correcting code you use and how many rounds of error extraction did you do in total, you can see that the optimum space-time, actually the minimum in space-time occurs at around 1 round per C0. And that was a very surprising result, and that is now something we need to make sure really works for universal circuits, right? Here I talked about Clifford circuits only. And it turns out, okay, so what do you need for universal quantum circuits? You have Clifford circuits, but you also need to throw in the magic states, or T-gates. Now, the way that it's typically done is you have a magic state distillation factory that produces these magic states, these T-states, at a desired fidelity. So, you might need to make a bigger factory if you want a higher fidelity of the T-state. But the point is that the magic factory itself is constructed out of Clifford circuits. And the other thing you need to do is you need to teleport the T-state, the magic state, into your main circuit. And so the question is, does this teleportation with its measurement and its feed-forward step really work in a fault-tolerant way according to our new scheme? Because what you need to do really is you need to, before you've gotten the syndromes for the rest of the circuit, you need to do this mid-circuit measurement and commit to a feed-forward operation. So you can only really make use of partial decoding up to that time. And the problem now becomes, at the next logical block, when you do your next teleportation of the magic state in, you might discover that your interpretation of the measurement here, based on your partial decoding, is inconsistent with future interpretations. And that is the fundamental problem that everybody was worried about in terms of universal quantum computation with this scheme. But it turns out that there is actually a way to restore the consistency of these measurements and feed-forward operations by applying the correct set of logical stabilizer operations to the input states in a way that restores this consistency. It turns out there's always a solution, and it turns out that at the end of the day, you can restore back to your correct output distribution. There is actually a formal proof that this works, and it's in this paper. And the main assumption is that you need fast classical decoding, and that is actually, still an area of discussion and exploration, because in some sense you do move some of the complexity of the problem to the classical decoding part, because now you have a big hypergraph, and I'll come back to that at the end. Some numerical experiments to prove this works at the level of circuits. Here we're creating and teleporting GHZ states. In one case, it's a transversal gate scheme with this algorithmic fault tolerance approach. In the other case, it's your classic lattice surgery approach. And indeed, if you constrain yourself to only have a single round of error correction, single round of syndrome extraction, you will see that the transversal approach does give you exponential error suppression with code distance, whereas this lattice surgery approach actually has an increasingly large error with code distance because it's not fault tolerant anymore with only one round of syndrome extraction. The final numerical experiment you need is to show that the state distillation factory works. And now, it's hard to simulate T-state distillation factories, but we did simulate the Y-state distillation factories. The circuit has the exact same structure. And the idea here, again, that as your code distance increases, this algorithmic fault tolerance approach applied to the factory does give you the correct ideal behavior for distillation. And indeed, you can also stack the distillation factories and make, kind of continue improving your magic state with benefits from this algorithmic fault tolerance approach of only one syndrome extraction round per Clifford gate in the factory. So this concludes the part about the algorithmic fault tolerance, and I will briefly now talk about the other dimension, which is the space savings. Now this is all about these quantum low density parity check codes, and the important thing is, it's a product code, and really talking about here about the memory block. Now you do need this, mediating ancilla and additional computational code patches to extract the logical qubits out of the QLDPC memory and do operations on them, and that costs you a little more. But without this part, the memory block itself can give you, in principle, savings of d squared in terms of how many physical qubits you need to encode a certain number of logical qubits. So in the surface code, that cost is d squared, and in QLDPC code, that cost is basically constant in d. Now, the codes we're talking about are actually product codes, and for very important reasons. So now, what is a product code? In this case, what we're doing is we're taking two classical one-dimensional LDPC codes and constructing the quantum code as a product of those. I'm not going to get into too much detail about how exactly you do the syndrome extractions here, but the point is that they are non-local. So in order to get an ancilla and do a syndrome measurement, you have to move a whole bunch of qubits across this code block. And the nice thing about the product structure is that it matches exactly the control structure of your qubit reconfiguration. The way that we move qubits around is with cross-acousto-optic deflectors, which allow us to actually permute rows and columns in sequence, and that makes the syndrome extraction for this QLDPC memory block extremely efficient. And the compilation of this hypergraph product code onto an actual neutral atom quantum computer looks like this. So these are not actual atom images, but this is these are the operations that would go onto the neutral atom computer in order to run the code. And the video is not running. Oh, there it is. So you can see these permutations of the columns that are done with our optic deflectors. So you can actually create an arbitrary arrangement of your ancilla in columns in log depth in log D time. And then you do your row permutations after that, and then you can do your syndrome extraction. Here's a numerical experiment that shows that this code block really is fault tolerant at the level of doing circuits to do the syndrome extraction with a threshold that's comparable to surface codes, but importantly with significantly improved logical error rate as a result of the space savings that you get. So for the same kind of physical error rate, you can make use of your qubits much more efficiently. So this is the numerical experiment. Now you can do some more analysis of the performance of the whole kind of processor, including these additional zones you need for doing the operations on the logical qubits, and you still get the significant space savings. And in particular, we did a few numerical experiments to show that even at the level of about 100 logical qubits, you already start to see significant gains in the number of physical qubits you need. So now if you kind of extrapolate, you can see that for 100 logical qubits, which is what we're targeting to start to do useful algorithms, which will cost us in a neutral atom processor about 5,000 physical qubits, that's already within range of QuEra's generation 3 QPU that we're building today. And to extrapolate further to 1,000 logical qubits, which will cost about 100,000 physical qubits, that's still within range of the neutral atom architecture that we have at QuEra and the underlying physical capabilities of devices that we expect. So the future looks pretty interesting. Now here are some outstanding questions about this particular work. So number one, can we do fast classical decoding for this algorithmic fault tolerance? And if that becomes time-consuming, how do you balance that against the time-consuming syndrome extractions? And maybe there's the sweet spot there. Second one is, can you combine this QLDPC approach with algorithmic fault tolerance to have the full-scale space-time savings? Could you really have a space-time cost that is independent of D? Or if that sounds too good to be true, what can the scaling be in the best case, in the best design? And this really will require a lot of co-design of the code and the hardware architecture and the algorithms. And we hope that you will engage with us on some of these design and testing problems between the error-correcting code algorithm and hardware design. And we hope that our newly deployed gate-based machines will be a focal point for actually validating some of these ideas and some of these architectures together with our partners and customers. So please come work with us, and this is QuEra.